All right, so if you have not watched the lecture video for day 67, be sure to watch the lecture video for day 67. I'm not going to go over everything that we talked about in the lecture video today. All right, so looking at number 1, suppose that the reaction system, which you see there, has already reached equilibrium. Predict the effect that each of the following changes has on the equilibrium position. Indicate whether the equilibrium will shift right, shift left, or will not shift at all, or will not be affected. So A says additional UO2 is added to the system. Which direction should we shift here? Well, if you noticed, we have a solid here where the rest of these things are gases. So whoever said that we will have no shift, very good. So again, we do not account for things that are pure liquids or pure solids. Another way to think about it is if you were to write up the expression that we have this, if it doesn't appear in the expression, then it does not affect the shift. That's probably the best way to think about this. Okay. All right, number 2, or letter B. It says a reaction is performed in a glass reaction vessel. HF attacks and reacts. So this word right here is huge. Reacts with the glass in the reaction vessel. Okay, so in other words, what's happening is we have this HF that is leaving the reaction to go react with something else. So we're actually removing some of the HF. So which direction will it shift if we remove some of the HF? That is correct. It will shift toward the removal. And in this case, the reactant is the thing being removed. So shift left. Looking at the next scenario, water vapor is removed. Okay, so water is on the product side. So same thing, if we were to remove water, it will shift in the direction of the removal, shift toward the removal. So in this case here, we will shift right. Oops. Again, we shift away from the addition, we shift toward the removal. And that goes for reactants, gases, energy. So when we talk about the energy here in a few minutes. All right, number 2, predict the shift in the equilibrium position that will occur for each of the following reactions when the volume of the reaction container is increased. So in other words, it goes from this to that. Okay. So what's going to happen? Let's say that we're at 1 atmosphere here and we have X number of particles. As soon as the container gets larger, we're still going to have X number of particles, but the number of collisions along the wall are going to be a lot less because they have to travel farther. There's a greater volume that they're actually occupying. So in this case here, we want to ask ourselves, which side has more gas particles? And it's more gas particles, not more particles. So in this case here, we want to shift in the direction that forms more gas particles. So in this case, we will shift left. In other words, what we're trying to do is increase the number of gas particles so that we can get our pressure back to where we were. Okay. Now, I had somebody ask earlier, well, if you do that, will your concentrations for your reactants be the same? Oh, no, they will not be the same. They'll actually be greater. And the concentrations for the product should be lower. But again, it's all about partial pressures. So that's what we're trying to focus on here. And it's a ratio. It's a ratio of those partial pressures. All right, so here in letter B, we have 1 and 2. So again, going from small to large. We want to shift in the direction that forms more particles. So B would be shift right. In C, we have two particles, no shift. However, what will happen is that as we go from here to here, then the temperature will change because the pressure is getting lower, the volume's getting higher, which will change the temperature in this case, since we don't have a chance to actually get our pressure back to where we were. Again, we're not going to have to calculate that. All of the questions asking is, which direction will the reaction shift to reestablish equilibrium? Looking at E, I'm going to skip D. How many gas particles do we have on the left? 0. How many do we have on the right? 1. So this reaction, again, going from small to large, we will shift toward the side that has more gas particles. Now, if we were going from a large to a small container, is it possible that we could shift to form fewer gas particles? Absolutely. Will we have any, or I'm sorry, is it possible that we would have no gas particles at the very end? Very good. We have to have some of these to be in equilibrium. So the key here is, even though we're shifting, we're not getting rid of all of them. We'll have something. Okay. All right. Let's look at number 3. It says an important reaction in the commercial production of hydrogen is given there. And it looks like they're all gases, and it looks like we have 2 and 2 gases. So the first one asks, gaseous carbon dioxide is removed. So make sure you know what carbon dioxide is. So this is being taken away. We're going to shift to the right, and it asks which direction the shift will be. So it will shift right. In B, it says that we are adding water. So that means that we will shift away from the addition. So to the right. The pressure is added by adding helium gas. Well, I do not see helium gas in this overall reaction. So since there's no helium gas in there, no shift. Again, a gas that does not appear in the reaction will add pressure to both sides of the reactants and the products, so it won't affect anything. Inert gases have no effect. The temperature is increased, and it says that the reaction is exothermic. So since the reaction is exothermic, which means that heat is a product, and we're increasing the temperature? Yes, we're increasing the temperature. So it's like I'm adding more hydrogen or more carbon dioxide. Treat energy like a reactant or a product, respectively. So in this case, since I'm adding more energy, we will shift away from the addition. Therefore, the reaction shifts left. And in this case, the K will change. Equilibrium constant. E says the pressure is increased by decreasing the volume of the reaction container. Again, we have 2 and 2, no shift. Number 4. What will happen to the number of moles? What will happen to the number of moles of SO3 in equilibrium with SO2 and O2 in the reaction? So be sure to AFQ here, ATFQ. All right, so we also have some information here that says we have delta H is a positive value, which means that energy is a reactant, which is kind of nice to know. As well leave it up there. All right, so oxygen is added, shift away from the addition. So since we're shifting away or shifting to the left to answer the question, sulfur trioxide increases. The pressure is increased by decreasing the volume. So we go from here to here. and we have 2 gas particles, 3 gas particles. So we will shift to the side with fewer particles. Therefore, the SO3 will increase. The pressure is increased by adding argon gas. Well, I don't see argon in this equation. So there will be no shift, which means SO3, no change. Letter D says the temperature has decreased. So let me get rid of that. And we're looking at E. So the temperature is decreased, which means that we are removing energy. So that means we shift toward the energy, which in this case means SO3 increases. Again, we're shifting toward the reactants because we're reducing energy and it's endothermic. E says gaseous sulfur dioxide is removed. So sulfur dioxide, which is here. So if we take that away, the reaction shifts toward the removal. So that means SO3 will decrease. Okay. All right, here's the best part. So it says ammonia is produced by the Haber process in which nitrogen gas and hydrogen gas are reacted directly using an iron mesh impregnated with oxides as a catalyst for this reaction. The equilibrium constants as a function of temperature are given. The question is this reaction exothermic or endothermic? Again, be sure that you solve for the shift first. In other words, figure out what is happening as we go from here to here to here. So my question is, these are the K values, because this is temperature. The K values are getting lower, -6 from a -3. That means that the products are getting lower. If that's the case, because again, this equals K, and K is getting smaller, so we have a direct relationship there, which means that the reactants have to be getting bigger. Therefore, the shift is away from the products and toward the reactants. Away from the products and toward the reactants. Therefore, or actually, now the question is, are we adding or removing energy? In other words, temperature is a measure of how much energy is present. So going from here to here to here, what has happened to the temperature? Temperature has increased, meaning that we are adding heat. Okay? Since we're adding energy, looking at what we just determined for the shift is the result of the addition of energy. As a result of the addition of energy, our K values have decreased, which caused the reaction to shift left. Therefore, my question to you is, if we're adding energy, which end, the reactants or the products, is the energy on? Very good. We shift away from the addition. We are adding, or the addition of the energy. Therefore, this is an exothermic reaction. Okay. Let me give you another scenario. Zap all this. Let's say that you are given, it's an endothermic reaction. The temperature increases. I want to know what is happening to K. Okay. So a different way to attack this. So start off, reactants, products. Where is the heat? Well, it says it's endo, so that means it's on the reactant side. What is happening to the temperature? Well, it says it's increasing. So if it's increasing, that means you're adding heat. And if you add something, you shift away from the addition. Therefore, when we look at our equation, our generic expression, if the arrow is shifting to the right, what is happening to the concentrations of the products? Very good. They are increasing because K is increasing and the reactants are decreasing. Therefore, we just answered the question. K is increasing. Okay? And it's all based on that information right there. So we have energy that we know is on the reactant side because it's endothermic. You're adding more heat, so you shift away from the addition. And as a result, if we're shifting away, K is increasing. Okay? Give you another one. Okay? Let's say we've got K is decreasing. The temperature is decreasing. Is this endo or exo? Okay, so we're looking here. Is this endo or exo? Again, start from the beginning. Products over reactants. Are the products increasing or decreasing? In other words, what is K doing? K is going down. Therefore, the products are going down. Use the information. If this is going down, this is going down for K. That's the easiest way to remember. The number on top is going to do the same thing as K. Therefore, the products have to be increasing. So my shift is to the left. If I'm decreasing my temperature, I am removing energy or removing heat. And this arrow tells me that I'm shifting toward. In other words, it is moving toward, okay? Moving toward the left side. Therefore, heat has to go here. Therefore, I have an endothermic reaction. Let's do another. Okay. Want to know what's happening to the temperature as K decreases and it's an endothermic reaction. Okay. So again, products over reactants. And we just said K is decreasing. So what are the products doing? Decreasing as the reactants are increasing. So shifting left. We know that this is endothermic. So it goes over here. So what's happening to the temperature? We are shifting toward the energy. Therefore, we are shifting toward the removal, which means the temperature is decreasing. Give you another. Exothermic, temperature decreases. What is K? Okay. So again, go reactants, products, temperature. I'm sorry, let's do exothermic. So exothermic is a product. So energy's over here. Temperature's going down. So that means we're shifting toward the removal. Therefore, K, based on the shift right, products are getting higher, reactants are getting lower, K is increasing. All right. I think we've done a lot here. Okay.